Welcome to this NPTEL lectures on robotics, basics and advanced concepts. In this week, we'll look at nonlinear control of robots. Okay, it will consist of 4 lectures. First, we will look at control of a multi-link manipulator. In the second lecture, we'll look at control of constrained and parallel manipulators and also Cartesian control of serial manipulators. In the third lecture, we'll look at force control of manipulators and also hybrid position and force control of manipulators. And we'll end this week with some advanced topics in nonlinear control of manipulators. Okay, so let's continue. Control of a multi-link manipulator. So the nonlinear control is a very vast field. Okay, we will look at only one particular kind of nonlinear controller called the computed torque, also called as feedback linearizing control scheme. Okay, so in ideal situations, I will show you that this kind of computed torque or feedback linearizing control scheme can give uniform performance everywhere in the workspace. Recall that a nonlinear robot, if it is controlled using a linear controller, cannot give same performance everywhere in the workspace. However, this computed torque scheme can give uniform performance everywhere in the workspace. So this computed torque or feedback linearizing controller uses the dynamic model in the control scheme. So what do we mean by dynamic model? We need to know the equations of motion of the robot. So we need to know the terms in the equation of motion, basically mass matrix, Coriolis, centripetal term, gravity term, and so on. And I will show you the better the estimate of the dynamic model, better will be the performance. There is a large amount of literature on this computed torque control scheme. It was first results were in 1972, but it was really popularized by Freund in 1982. Okay, so let's start. So as I said, in the control law using computed torque scheme, it consists of 2 parts. So that is why it is also sometimes called control law partitioning. And we also need the equations of motion of the serial manipulator. So the equation of motion of a serial manipulator can be written as tau is equal to m into q double dot plus centripetal Coriolis term plus gravity term. And if we know some, or if we have some idea of the friction, we can add the friction term also. Okay, so the scheme starts as follows. So we can write this n by 1 vector of joint torques as some alpha into tau prime plus beta. Okay, so this is like multiplication by some alpha, okay, plus some bias term. So scaling and some bias term. If we choose alpha as mq, which is the mass matrix, beta as the Coriolis centripetal term plus the gravity term plus the friction term, then if we substitute alpha and beta in this equation, we will get alpha tau prime plus beta will be equal to mq double dot plus cq dot gq plus fq. So everything will cancel out. This beta c plus g plus f will cancel out on this side. And then mass matrix is invertible, so we can remove the mass matrix from both sides. And hence we will be left with one equation, which is tau prime is equal to q double dot. Okay, so this is the starting point of this computed torque control scheme, or using what is called as control law partitioning. Okay, and as you can see, what have we done? We have a nonlinear system of equations for the dynamics of the robot. We have chosen to implement the torque which is going into the robot as some alpha tau prime plus beta, where alpha is chosen as a mass matrix, beta is Coriolis plus gravity plus friction. Okay, and we are left with tau prime is equal to q double dot. So the equation tau prime equals q double dot represents a unit inertia system with input tau prime. Okay, so see, there is no mass matrix Coriolis gravity term. So it is like as if tau prime is equal to I times alpha. alpha is the angular acceleration, where I is identity. Okay. And what have we done? We have used the dynamics represented by alpha and beta. Okay, so we have chosen alpha as mass matrix, beta as that C plus G plus F. And effectively what we have done is all nonlinearities and coupling are cancelled, and the original nonlinear equations transformed into n decoupled linear equations. So we have n decoupled linear equation, tau prime is equal to q double dot. Next, we can choose tau prime as qd double dot plus kve dot plus kp e of t. So this is nothing but the PD control with this acceleration feed-forward term added. Okay, so if you now substitute tau prime is this into this tau prime equals q double dot, and then take q double dot to the other side, we will be left with the error equation, which is E double dot plus kv E dot plus kp E of t is equal to 0. Okay, so how many such equations are there? There are n such equations. Okay, and E of t is nothing but the desired joint as a function of time, q dt, minus the measured joint motion as a function of time. And if you now choose kp and kv as positive definite diagonal matrices, okay, so then all these E1, E2, all the way till En, they are decoupled. Okay, and we can choose Kp and Kv to get critical damping at every point in the workspace. So remember, in the case of linear control, I had shown you for a single link that Kv, if is equal to 2 times square root of Kp, then we get critical damping. So we can choose critical damping or over damping or whatever we want to get the desired E of t as a function of time. So in block diagram, what we have is a robot. The input is torque. We measure Q and Q dot, okay, and we take this Q and Q dot and compute C plus G plus F. Okay, C Q Q dot G Q plus F Q. Okay, so this block here means that often we do not know exactly C, G, and F. Okay, so these are estimates of the Coriolis term, gravity term, and friction term, and the estimates of the mass matrix. We can also take this Q and compute M of Q, okay, mass matrix and Q. So what you can see is this dotted line here, okay, this portion requires the use of the dynamic equations of motion. We need to know what are the model-based terms. We can also take this Q and Q dot. So if you do Qd minus Q and multiply by Kp, okay, and then Qd dot minus Q dot multiplied by Kv and add to Qd double dot. At this place, we'll have tau prime. So basically what we have is tau prime into alpha plus beta is equal to tau. Okay, so the box which is dotted here is error driven. Okay, it is purely driven by Kp and Kv, so it is similar to the modified PD control scheme. Okay, so there are two partitions, one is which is PD control and one which is model based. So the ideal performance is not possible simply because we do not ever know the mass matrix, the Coriolis term and the gravity term and friction term, especially the friction term, very well. Okay, there are also one other property which is a little bit more complicated to understand. We require some time to compute this alpha and beta. Okay, so as you can see, this is alpha and this is beta. So we need to measure Q dot and then use it to compute this mass matrix and C plus G plus F, but it takes some time. So the torque which you are getting is based on a previous measurement, maybe a little bit behind. Okay, so hence it will never be exactly cancelling. Okay, so as I said, only the estimates of mass, matrix, Coriolis centripetal term, gravity, and friction term are available. That's why we have used this hat. Okay, and in the figure, the box with the cross is what is shown as hat. Okay, so the estimates because of the estimates, the error equations are no longer linear and decoupled. Okay, that we can show. So for example, if the alpha is m hat of q and beta is c hat plus g hat plus q hat, then you can work out the error equation, which is E double dot plus kbe dot plus kpe will be, now there will be a right hand side. So it will be m minus m hat q double dot c minus c hat g minus g hat f minus f hat. So m, c, g and f are the actual dynamics. Okay, whereas m hat, c hat, g hat and f hat are the estimated dynamics. That is what you think. Okay, and it is entirely possible you think the mass is, let's say, 5 kg, but then somebody has drilled a hole somewhere and the mass has decreased. So the estimated mass matrix will be different than the real mass matrix. And as you can see, if m minus m hat, c minus c hat, g minus g hat, f minus f hat, all these things are exact zero, which means what? I know exactly what is the mass, Coriolis, gravity and friction terms. Okay, then we have again exact cancellation and we are left with a second order linear ODE in the E of t. Okay, so what else can we say? If my estimates are good, okay, meaning what? This m minus m hat, c minus c hat and so on are small, then what we have is the linear second order ODE subject to a forcing term on the right hand side. So if the forcing term is small, then the eventual performance of the system, eventual performance of E of t will be also small. Okay, so E of t will be small if the estimates are good. So there are some special cases in control law partitioning. One is if alpha is U, or alpha is the identity matrix. So we are not going to assume any mass matrix. We think that it's an identity matrix. And beta is G of Q. So this is called gravity compensation. Okay, so if alpha is U and beta is 0, then we can get to PD control scheme. So beta is GQ means, remember the right hand side there is a G and then you have alpha tau prime plus beta. If beta is G, the gravity terms cancel out from both sides and the system will behave as if there is no gravity. Likewise, if alpha is U and beta is 0, you can show that you will get back the PD control scheme, very straightforward. There is also a very well-known control scheme which is based on the following observation, that we can compute alpha as a m of qd, where qd is the desired trajectory. Okay, so beta is computed as c qd qd dot, g qd and f qd qd dot. Okay, so the model terms alpha and beta are computed according to a desired trajectory and they are not in the feedback loop. Okay, so if you know the desired trajectory, we can compute or pre-compute this mass matrix, Coriolis term, gravity term and friction term. Okay, and hence there is no issue of computation time. Okay, it will be just reading from a file, okay, or reading from a lookup table. However, there is no exact cancellation in any of these special cases. Okay, but what is the hope? That QD and Q will be very close to each other. Hence, the estimates will be very good. Okay, so M minus M hat will be very small. C minus C hat will be very small. Okay, but theoretically, there is no exact cancellation in any of these special cases. There is no decoupling and there is no linearity. Okay, but as I said, if the estimates are good, then the right hand side is small. And what you can see is that performance will always be better if you do not use any model. So if you don't use any model, which means a PD control scheme, then alpha is U and beta is 0. Okay, then if you use some model, you have M minus M hat. So you have some smaller number. Okay, so performance is always better with some model than with no model. And no model is PD control scheme. So this can be seen to be borne out by simulation and experiments, which we will show. So let's start with some simulation results. So we have a planar 2R robot shown in these two configurations. So initially it is like this at some xi, yi, and it goes to xf, yf. Okay, again, just like in the previous week, we have this 2R with link parameters M1, L1, R1, and I1, and M2, L2, R2, and I2. There is a torque acting in first joint. There is a torque acting at the second joint. So we go from xi, yi to xf, yf in some time and come back. Exactly the same numerical experiments that we did in the previous week. And we are going to use the same parameter values for the link 1 parameters and link 2 parameters. And again, there is a payload of 2.5 kg at the end. Okay, so this link length is 1 meter. The CG is located at 0.773. The mass is 12.456 kg. And the IZZ inertia of this link 1 is 1.042, and so on. Okay. So as I said, the tip moves from 0.55 meters on the y-axis to 1.45 meters on the y-axis and back to 0.55 meters. So it is going exactly against gravity and it is coming down with gravity. Okay, so as we had discussed earlier, there are two cases. One is fast motion, which is total time is 2 seconds. Another one is slow, which is total time is 2 minutes. So the basic idea is we will use the same results which we saw for linear control using PD controllers, and then we will see what happens when we use a nonlinear control law, okay, based on computer torque. Okay, so the same set of parameters, same trajectory, everything is same. So we have a smooth Cartesian cubic trajectory. So basically the desired is x should be always 0. Y should go from 0.55 to 1.45 and back. These are two cubic curves which are patched together. From inverse kinematics, we can find out theta 1 desired and theta 2 desired. Okay. These also will be smooth curves. Okay, C2 continuous curves. So as I said, the theta 1 desired and its derivatives are obtained using inverse kinematics and inverse Jacobian. And we will now present simulation results for a PD control scheme, which is basically a linear control scheme applied to this robot. Then a feed-forward controller with exact knowledge of the model parameters. So although we have M hat, C hat, Q hat, the hat is because we are not using the measured Q and Q dot and so on. We are using the pre-computed desired trajectory. I will also show you some results for model-based controller with 10% error in mass and 5% error in location of the CG. Okay, so we do not know the masses of the links and inertias exactly. Let's assume there is a 10% error and a 5% error in the location of the CG. Notice that we are not assuming any error in the link lengths. Okay, if there is error in the link lengths, then we can never trace the desired trajectory. Okay, and last we will look at Cartesian control scheme, which is discussed later. Okay, we will see what is the equation of motion when we derive the equations of motion using the Cartesian or the end effector coordinates, position and orientation. In all of them, all these above simulation, we will choose KPI and KVI as corresponding to omega as 1 as 85, omega 2 as 75, and the damping is 2.0. So basically we have an overdamped system with some chosen natural frequency. We can choose other natural frequencies and dampings also, but let's see what happens when we indeed choose these values. Okay, so as I had shown you, the error for the fast motion is theta 1, theta 2 error. So it goes like 0.0, almost 0.03 radians. Okay, and on the negative side, again 0.025 radians. In X and Y also, recall that desired X should be 0. I should just go along the Y axis. the desired trajectory. But we do indeed move along the x-axis by some amount, and it is of the order of 0.0, more than 0.02 meters. So like almost 2 centimeters, between 2 and 2.5 centimeters. Okay, the y trajectory is also not exactly following the desired trajectory. Okay, so the x is of the order of 0.15. Okay, so 1.5 centimeters. And in the y direction, the maximum error is more. It is of the order of between 2 and 2.5 centimeters. The torque profile looks like this. So we start from 0 and it goes to some 225 Newton meter for tau 1, and it is lesser for tau 2. It's of the order of little more than minus 150 Newton meters. Okay. So as you can see, important thing to notice here is there is some kind of a peak here, and then it just comes back and then again rises. Okay. If you do PD control with slow motion, which was 2 minutes, and as I had shown you, the theta error in theta 1 and theta 2 are much smoother. They are also less. Okay, the error in x and y are also much smoother and less. And more importantly, the torque at the two joints are smaller. Okay, and they are smoother. So this we had shown earlier. And the reason was that if you move slowly, the nonlinear terms are smaller. Hence, their effect is smaller, and hence the robot can track better. Okay, the desired trajectory. The tip of the robot can track the desired trajectory better. So, summary: the maximum error in the joint variable in case of fast motion, which is what we will look at from now on, is 0.03 radians versus 0.02 in slow motion. Okay, and 0.023 meters in fast versus 0.016 meter in slow motion. Okay, so as I said, in the fast motion, the nonlinear inertia centripetal Coriolis terms are larger. Okay, linear PD control is less effective as expected. The maximum torque is also larger, approximately 225 Newton meter versus 145 Newton meter. The torque is larger in fast motion, again due to the nonlinear terms in the equation of motion. Okay, the curves are much smoother in slow motion, and next we will present the nonlinear control simulation results. As I said, there are three of them. One is exact cancellation but feed forward. Then there is one with 10% error in mass and 5% error in location of CG, and one is Cartesian control using Cartesian equations of motion. Okay, so here are plots. So let's just go over it. So, and we will look at the fast motion, because in the fast motion for PD control, the errors were larger. So let's see what happens when you use nonlinear controllers for the fast motion. So the error in X and Y, as you can see, is really, really small. It is like of the order of 10 minus 10 meters. Okay, so in feed forward controller, these are the two plots which show that the error in X and Y is very small. Okay, there is some peak here when it is changing direction, but nevertheless, even then it is like 10 minus 10 meters. The torque is also much, much smoother and very similar to the slow motion torque. Okay, it is very smooth, it comes down and then again increases. Okay, so as you are going up, the torque required is less because it has acquired speed, and then while it is coming down, you have to change the direction of the torque again. Okay, when you have estimates error of 10% and 5%, as you can see that the error is much larger than the feed forward with exact cancellation, with exact parameters. Nevertheless, it is still smaller. It is of the order of 10 minus 4 meters in X and Y. Okay, so what is 10 minus 4 meters? It is like in point something millimeters. The torque is also very, very nice and smooth. It's very similar to the torque obtained for the feed forward controller. Okay, and also it is very similar to the slow motion torque. There are no peaks and sharp changes in the torque profile. In the Cartesian controller also, it is very small. Okay, the no changes in the torque profile also, and the numbers are very similar for errors in X and Y. So what is the moral of the story? Even with 10% error in masses and 5% error in location of CG, the error comes down from something like 2 or 2.5 centimeters to less than a millimeter. Okay, and this is shown both in computed torque controller and also in Cartesian controller, and moreover in computed torque controller with uncertainties. If you know the parameters exactly, then it is much smaller. Okay, several orders of magnitude smaller than when you have an estimates of the mass and location of CG. Okay, so in summary, the feed-forward controller without modeled uncertainty is very accurate. The computed torque with 10% uncertainty is not that accurate. However, it is more accurate than PD. Okay, remember in PD it is of the order of 2 or 1 to 2 centimeters. The torque profiles are smoother. It is similar to PD control for slow motion. And why? Because the effect of nonlinearity is reduced in this computed torque schemes. Okay, we are somehow cancelling out the nonlinear terms in the equations of motion. So the 2R robot behaves more like a linear system, okay, with computed torque schemes. And it is very similar to the slow motion, because in the PD with slow motion, it was moving slowly, the nonlinear terms were not so large, and hence the errors were smaller. Okay. Even one thing to note, that even with PD with slow motion, the errors are larger than the one with computed torque schemes. Okay, so summary of simulation results. The PD or PID control scheme is not suitable for high-speed applications, and the errors can be large. Okay, to reduce errors, we need to perform trial and error. We can change the controller gains. Okay, so I have chosen omega 1 was 85, omega 2 was 75, psi was 2.0, and then obtain KPI and KVI. We could play around with that. We can do trial and error to reduce the errors. Okay, the performance for slow speed motion is better, and one can get smooth torque profiles. Model-based schemes show improved performance in simulation. The torques are lower and the profile of torque is also smoother. The lack of knowledge of parameters degrades the performance to some extent, but not a lot. It is still better than PD without any model. The computation times for model-based controllers are larger. I haven't shown you here, but as you can see, we need to compute some 6x6 mass matrix and Coriolis term and centripetal term. But with modern, newer processors, it is not very serious issue. Okay, originally maybe 30 years back, when the processors were not so efficient, okay, this was an issue. Now let's look at nonlinear control for an actual robot. So I am going to present to you some experimental results on nonlinear control. Okay, so this was a robot on which my two students worked on it a long time back. So the robot is a 5-axis servo manipulator. So why where are the 5 axes? There is one joint, one motor which is in the vertical direction. Then there are 2 motors which are located in the same plane here. One is for elbow and one is for shoulder rotation. So this is called elbow extension and this is shoulder swivel. Now, if you have both these motors here, in order to rotate this link, we need a mechanism. Okay, so basically there's a 4-bar mechanism connecting one of the motors to this linkage. So one of them rotates this link and one of them rotates the other link, and then this arm will also go up and down. Okay, the reason why these 2 motors are kept on this plane is to minimize the inertia seen by the second motor. First motor sees both these motors' inertia, but they are located exactly equal distance from the axis, so that's a nice design. And then this second motor does not see the third motor inertia. So in a typical serial robot, the second motor will see the inertia of the third link also. In this case, not so much. But there is a problem, or there is a complication. In the sense, the drive is not exactly like a serial robot. It is a mixture of serial and parallel robot. Okay. The original robot had motors with large gear reduction, and due to this large gear reduction, there was significant backlash and friction in the gears. Okay. The motors also had encoders and tachometers, tacho generators, to measure joint rotation and velocity. Okay, so in feedback control, we need to measure the theta, q, and q dot. These were measured using these optical encoders and tacho generators. The existing control scheme for this robot was that the voltage applied at the ith joint is proportional to the error theta id minus theta I multiplied by a proportional gain minus kvi theta dot. Okay, so there is a small difference between what we have seen till now and this, which is that theta d dot is not being used. Okay, so it is kv into e dot. E dot is theta d dot minus theta dot. Now theta d dot is 0, so hence you have a minus kv into theta dot. Okay, so this is the voltage which was applied at motor I. Okay, the subset of PD control law is being used. So basically, we are not using theta dot and theta double dot. Okay. So first thing that we did was we modified the existing joint rotation, which is theta ID, to include the effect of theta I d double dot and theta I d dot. So this is a clever way of doing it, that if you now, instead of theta id, we say we will supply theta id star, where theta id star is theta id plus 1 over kp into theta double dot desired plus kv by kp into theta dot desired. So if you substitute back this theta I star in this equation instead of theta I, what you will get is theta I double dot plus kpi error plus kvi into e dot. Okay, so what have we done? We have modified the desired input somewhat to obtain the standard PD control law which we are familiar with. Okay. So we can also modify the existing controller to a model-based control scheme, not exactly a computer talk model-based control scheme, which cancels the nonlinearities. We modify theta id with some voltage due to a model divided by kpi plus the original theta id plus this theta double dot divided by kpi and theta dot into kv by kp, okay, for each one of the 5 joints. Okay, and this voltage due to the model is based on the equations of motion. So we know what is the desired trajectory. We know theta d double dot, we know Coriolis term, we know gravity term. We compute the torque which is required to obtain this theta d double dot and theta d dot and theta d. That is called tau model. Okay, and this voltage due to the model is corresponding to this tau model. Okay, and this is obtained with available motor characteristic charts. So the above control scheme, once you substitute theta I d star and tau model and vi model, it will look like tau equals tau model. The input to the motor torque is equal to the torque due to the dynamics, which is the model part, and the PD part. Okay, so as you can see, it is not alpha tau prime plus beta. It is some bias term, okay, which is beta plus some PD term. Okay, so the model parameters required for theta id star, okay, like m, c, link lengths, all these things were obtained from the CAD model of the robot. So this robot was designed in this place, so which had a CAD model, and we could obtain this. So finally, what happens is we are going to use theta I star instead of theta id. theta ID star instead of theta ID. Okay, so the reference input is changed. Okay, and what is the advantage of doing this? We do not have to touch the electronics of the hardware. All we say is that the desired trajectory is changed, and the desired trajectory now somehow takes into account the theta dot, theta d double dot, and the model to some extent. So what was the desired trajectory? We traversed from 0, 0, minus 90, 180, 0 to 30, 40, minus 60, 180, 0 and back. Okay, so we start from some initial joint angles to some final joint angles and come back. And we assume that the total time was 2 seconds going from this point to this point and another 2 seconds to come back. So it turns out that the initial 2 seconds is against gravity and the final 2 seconds is aided by gravity for this robot. We generated smooth trajectories with 0 initial and final velocity. The sampling time is 5 milliseconds, or a set point is generated at the frequency of 200 Hertz. Okay, so this trajectory is typically faster than the usage of that robot, which was designed for. The robot was not designed to go this much distance in 2 seconds. Okay, now let's look at some of the experimental results that we have obtained. So in this plot here, the solid line is the desired theta 1 desired. Okay, so it's a nice smooth cubic profile up to some place and cubic profile from 2 to 4 seconds. So it goes against gravity and comes back. So the first dashed line, okay, is the trajectory or theta 1 due to the model when the model based terms were included. The second small dotted line is what happens when you do a PD control. Basically, we modified theta I star to include the theta d dot and theta d double dot. And this one is the includes the model. So what you can see is the difference between the desired and model base is smaller. Okay, the difference between the desired and the PD is also larger than the difference between the desired and the model base. And that is especially so when it is coming down with gravity. The plot on the right hand side shows the difference between Q1D and Q1 obtained for model base and Q1 obtained for PD. So as you can see, for model base, the error is like maximum error is between 1 and 2 degrees, whereas for PD, it is between on the other side, it is like 4.5 degrees, but while going up, it is like 2 degrees. Okay. For joint 2 also, we can compare the errors, and I'm not showing you the trajectory. There also the desired is smooth, and we record what the joint 2 is doing from the encoder and plot the theta 2 as a function of time for PD control and theta 2 as a function of time for model based control, and then we subtract theta 2 from the theta 2 desired from in both cases. So this shows the error between theta 2 in PD control and theta 2 in model based control with respect to the theta 2 desired. And as you can see again that the model base is smaller. Okay, so here it is like 2.5 degrees. This is the maximum is like 1.5 degrees. Likewise, for joint 3, we can plot the error when we execute PD control and when we execute model-based control with respect to the desired trajectory. So here you can see that the difference is not that much. Okay, so it is like in one case it is like 1.25 and this is like 0.75. On the other side, it is more or less same. And one of the interesting thing that you can see is at some place there is some resonance. Okay, there is some oscillations which are happening. Although we have chosen the gains such that it is overdamped, nevertheless you can see some oscillations. Okay. So the maximum theta 1 error is reduces from 5 to 2 degrees. Theta 2 error reduces for model base, not much difference in theta 3. And in joint 4 and 5, which I'm not showing, there is almost no difference between PD and model base. Okay, and there is a reason. The joint 4 and 5 are the last two joints. They don't see any too much inertial Coriolis and other effects. Okay, it is moving a very small mass, the last two joints. Whereas the first joint is moving all the links after the first joint. So it sees a lot of inertia, Coriolis and other effects. So in summary, the multi-link serial manipulators are nonlinear systems. We know that from the equations of motion. The linear PID control law not expected to give uniform performance at every point in the workspace, and that we can see. The nonlinear control scheme using control law partitioning, okay, which is error driven plus model based portion, performs better. The ideal computed torques method leads to decoupled linear double integrators with uniform performance everywhere in the workspace. Remember, it was tau prime is equal to q double dot. Okay. If we do not know the model parameters well, that means m is some m hat, c is some c hat, and so on, then we don't get decoupled or linear set of equations. Okay. Nevertheless, the performance is expected to be superior to PD or PID controller, as I've shown. And basically, the model-based controllers are superior. Okay, and I've shown you 3 experiments of theta 2, theta 1, theta 2, and theta 3 experimental data. And similarly, I've shown you for simulation also. Okay, so with this, we come to an end of this lecture. In the next lecture, we'll look at control of constrained and parallel manipulators.